Hi class, this lesson is on unbalanced forces with a focus on tension and friction. Our focus today is using Newton's second law quantitatively and qualitatively, solving problems involving forces, and we're definitely going to describe solid friction by coefficients of friction. Although most of this is review today, we are going to get more in detail when we use Newton's second law and solve problems involving force in other situations. So this is our kind of base before we move forward. So really understanding this is important, which is probably why we hit it so hard last year. Um, First we have just this warm up, very simple. There's a force free body diagram on an object, and we need to calculate force and acceleration. So I'm going to pause this video. I want you to work through this, just kind of a refresher, and replay when you finish. All right, so I've included the downward and upward forces on this free body diagram, the gravitational force and the normal force, although they're not set to scale because they should be significantly larger, but we just know the most important thing is that they are equal. The object is being pulled to the right, but it's not falling through the desk, nor is it being lifted any bit. So we know that since it's not being accelerated upward or downward, that it has a net force of 0 newtons. Next, in the horizontal net force, we have a rightward pulling force of 10 newtons. We probably have a frictional force, I imagine, of 4 newtons. So we have a net horizontal force of 6 newtons. And I should say it's to the right, just in case we don't recognize what direction it's going in. Of course, the picture kind of shows it, but that's important to note. Now, when we calculate the acceleration, we already know that the net force is equal to mass times acceleration. One thing we have to think about that this is like the net acceleration. So when I say net acceleration, when we measure an object's acceleration, that is the acceleration we're using when we put in the net force equals ma. Now, where we get the net force comes from those like micro individual forces, such as the 4 and the 10, but the net force, that's what we observe happening, and that's the 6. So the 6 newtons is equal to m times a. Mass is 5 kilograms, so we get an acceleration of 1.2 meters per second squared. All right, so this is going to come around constantly. Let's move forward though. Let's start talking about, for example, the frictional force. Let's say like the 4 newtons. So frictional force occurs due to like the rough edges of any surface. And even though we like to say that there are some surfaces that are really smooth, like my desk feels smooth compared to, let's say, sandpaper, but still, when I move my hand over the desk, I still feel the friction. When you rub your fingers together, hands together, and do like a rubbing motion, then you still feel heat. So there's still some friction that's occurring, some energy that's being pulled from your movement, and that's due to friction. So any surfaces have uh, this type of layer on it, just some more than others. So I want to actually take a step back and look at a effect that we may have done in the past, and that is this one right here. So in this interactive, we have a stick man of some sort, and they are about to push a fridge. So when I start pushing it, and I have all the labels with values, masses, speed, everything. So when I start pushing it, let's say at 50 newtons, it's going to push back at 50 newtons. That means the fridge is sitting on the floor, it is not moving, and it's creating an opposing force that's equal to the pushing force. If I go to 100, it continues to create a opposing force that's equal to the pushing force. This is what's called static frictional force. This frictional force occurs when you are not moving. So as highlighted by the speed being 0. So you are not moving. And static is another word for like constant, but specifically like just stationary. I like to think of static as stationary when we're talking about frictional force. As you can see here, whether we're being pushed at 50 newtons or 193 newtons, in this case, our object is not moving and the force is equal to the pushing force. The frictional force is equal to the pushing force. So there is actually, so when we talk about force of friction static, we might do F of F comma S. There is a less than or equal sign in this, and this is equal to mu, which is our static frictional coefficient, times R. And R, right, we already know R is our normal force. And this is what we call our coefficient of static friction. We should have already learned this. And this less than or equal sign shows that the frictional force is always going to be equal to the pushing force until it reaches some maximum. And that's where that less than sign goes the way. Once it becomes an equal sign, kind of if I were to say, what about, let's create some space. What about if the force of static frictional, let's say max, that would be equal to mu s times r. That's when it becomes the maximum point. So let's look at what that looks like on this picture. So I can go even more, 150 newtons is opposing equal. It's still less than or equal to, less than or equal to. And I believe if I push one more newton, then I'm going to hit, I'm going to go above the point. So I believe in this case, 200 newtons is going to be our maximum static frictional force, because when I push one more newton, then we end up, our frictional force decreases. That means that our static frictional force has now been overcome, and it's riding on the top. Now, it's kind of hard to why is it doing that? Well, I want to go back to this picture and remind ourselves of certain situations I like to compare to. The one that I like to compare to, comparing static to dynamic frictional force, is like a boat in water. So if we have a boat in water, that's our boat, that's my boat, and it's not moving, then what does the boat do, right? The boat kind of sinks and it sits in the water. Similar to how this picture, the grooves might find this comfortable spot and they'll sit down in this spot. But once it starts going faster, and so let's make my boat, let's do this, and now it's going faster, the water is going to sit more on the bottom, and it's going to kind of hydroplane. Imagine a speedboat. And you know how a speedboat shoots off and the front end lifts above the water and only the back end sitting on the water? That's the way I like to think of what dynamic frictional force is. So once it starts moving, it is able to kind of screen across the top of this layer, and it doesn't sit in the grooves of the surface that it's on. And so let's look at that again and now it's moving. And one thing you'll notice right here is the frictional force has now decreased. The static frictional force was able to go up to 200 newtons, but the dynamic frictional force went down back to 150. So that tells us something about dynamic friction, and specifically this coefficient of dynamic friction, because let's go back and look at this. And in this case, it's a little different. But now we have dynamic frictional force where V is greater than 0. We don't care about acceleration. We don't care about that. We just say, is this moving? So in this case, there is a speed. The equation, force of friction dynamic, sometimes it's called kinetic, is equal to, there's no less than or equal to in this, it's just equal to mu d times r. And so we know that if an object is moving, the frictional force is constant. It doesn't matter if it's moving slow or if it's moving fast, the frictional force is constant. The r is not changing and the mu is not changing. So the frictional force is not changing. So whether it's being pushed and it has some speed right here, or and the net force is 0. In this case, right, net force is greater than 0 and V is greater than 0. So the frictional force is dynamic. And in this case, although we can't really see it, this one is still moving as well. And while that one's moving, the net force is 0, but the velocity is still greater than 0, so we're still dealing with dynamic friction. So whenever an object is moving, we deal with dynamic friction, and that's the kind of the easy one. The static friction is dependent on the pushing force until it reaches the maximum point. So in order to kind of make more sense of this, let's do some problems. So I have an example problem. The Rafflesia Arnoldi, if that's how you say it, in Malaysia, probably not how you say it then, is a flower. Now, I don't know why I'm using this example, but we're running with it. So it's the largest flower in the world 1 meter across and with a mass of 11 kilograms. If the coefficient of static friction between the floor and the forest floor, so I guess they're in a forest, is 0.76, find the minimum force you would need to apply to set the flower in motion. So first, we want to draw a free body diagram of the flower, and then we want to calculate. So yeah, free body diagram, sure, you're a sphere. So we have some force of gravity, we have some normal force. We also know there's a frictional force going backwards, and we want that to be called our force of friction static max. And we know that we're pushing slightly greater than that, so our F applied. And it's just about to move because we are reaching the maximum static frictional force. So we've drawn the free body diagram. We know that our frictional force, static maximum, is equal to mu s times r. And we need to solve for r, and we already have mu s. So okay, so on the side, we have our static frictional coefficient is 0.76. We have our mass is equal to 11 kilograms, as shown up here, right? There's 0.76, there's 11 kilograms, and we have our equation already set up. So we just need to find our force of gravity, therefore our normal force, right? So R is equal to Fg, and that's equal to mass times gravity. So we have 11 times 9.8, and that's 107.8. So R is equal to 107.8 newtons. And I can plug that in. And you might say, why are we using normal force? Why aren't we using the force of gravity? And the question really comes into, imagine you have an object near you and you push it against some surface. You might feel that friction when you push it against the surface. Now this is a silly thing to do, so don't do it. But if you take that same object and put it on a vertical wall and drop it, what is it going to do? It's going to fall. The surface that you just put it next to does not create a reactionary force because there's no gravitational force pushing down on there. So it doesn't slide down. But imagine you take that wall, or you take your notebook and you create an angle that has a mostly vertical way. So like as if you were to draw, like create a surface like with this angle, and you put your object on this. Well, you would definitely feel some friction, but not nearly as much as if it was a flat surface. And so we need to learn how to use the normal force in these situations, because the normal force is the force that the surface is pushing against each surface. So we'll talk about that more when we do inclined planes, but just know that it has to do with how much is the surface pushing against the other surface. Okay, so I'm going to plug my values in. I have 0.76, I have 107.8, and that's my force friction static max. You can probably find a better way to write that. If it was just me, I might just write F of F. 0.76 times 107.8, I get 81.9. So this is 81.9 newtons, and we are good. Now there's two more questions because it gets, we move to dynamic friction, and then the last question, which I might just leave you to do on your own, is start thinking about it as, hey, we can incorporate kinematics into this situation because it will be moving now, and since it's moving and there's an acceleration, then we have motion math. All right, once moving, you continue to pull on the flower with the same force calculated above. So the 81.9 newtons. Calculate the acceleration of the flower. The coefficient of dynamic friction between the flower and the floor is 0.44. As previously stated, we said that the dynamic frictional coefficient will always be less than the static frictional coefficient when dealing with the same two surfaces. As shown by like this frictional force is 144 newtons, and that's your dynamic frictional force, and this frictional force is 193 newtons because that's your static frictional force. Using that same example of like the boat in water or the grooves of a surface to help hold things in a static motion, in stationary motion, so not moving at all. So let's do our example, draw a free body diagram. I'm going to start you off with a free body diagram, and I'm going to let you do this problem on your own, and then we'll revisit. So I guess I've been a sphere before. Let's be a sphere again. So I have my R. Good news is I already know my R value. It's 107.8. So similar to how I like to draw values on my other diagrams, I do the same thing here. And it says, I am continuing to pull the flower with the same force calculated above. That's my 81.9. So I would say this is 81.9 newtons. And I don't know my dynamic frictional force. So I need to solve for my dynamic frictional force. And then I need to calculate my acceleration because that's what it's asking for. So I'm going to pause this and I'm going to let you use your notes, try to solve this, and let's revisit it shortly. All right, I'm one step closer. I found my force of friction dynamic to be 47.4 newtons. And again, I would go to my diagram and I would write it down, and then I'll continue solving. So again, I'm going to pause this. See you soon. So I've set my net force equals MA. I also know that my net force is equal to my applied minus my dynamic frictional force. I should be a little nicer and do this. Although I know that my acceleration in my y direction is 0, it's still proper to kind of continue with this subscripts. And if I do this, I get an acceleration that's equal to 3.14 meters per second squared. And that's how you would kind of follow through this process with dynamic frictional force finding acceleration. Now I could keep on going and say I have my acceleration from rest. How far does the flower move in 3.75 seconds? So I can say, hey, I have my acceleration in my horizontal direction. I'm at rest, so my initial velocity is 0, and I know I have my time. So how far do I go? And you can use motion math to kind of continue down this path. But I'll let you do that on your own. And I will see you in class.